In part 4 of my lecture on correlation and regression, I'm going to be looking at agreement. This comes under the heading of misuse of the correlation coefficient, when people tend to use correlation coefficient when they shouldn't. Because it's not always appropriate to use the correlation coefficient, because the correlation coefficient R measures the strength of a relationship between two variables, but it doesn't say anything about the agreement between them. So, for example, if x and y are different measurements of the same thing, that might be, for example, the weight measured on two different sets of scales, so they're both measurements of weight of the same thing but measured in different ways, then we would expect a good correlation anyway. So the correlation coefficient will always be close to 1, and the correlation will always be significant if these are two measurements that are supposed to be the same. So correlation doesn't tell us anything in this case. In fact, you can still get good correlation even if x and y don't agree. If the two scales are in disagreement, it doesn't mean that they can't be correlated. Here's an example, for example, of patients weighed on two different scales. On the vertical axis, we've got the weight using set B of scales, and on the horizontal axis the weight using set A of scales, and I've put on there the measurements which show an R squared of 0.96, showing an excellent correlation. And indeed I've plotted a trend line through the data which shows a nice linear relationship between the two. However, if you look carefully, the equation of that trend line, y equals 0.75x, says not that y is equal to x, but y is equal to 75% of x. That's much clearer if we put on the line of identity. The line of identity is the line in which y equals x, and you see all these points are very much below the line. In fact, they are 25% below the line, as indicated by y equals 0.75x. So set B reads 75% of set A. That is, B is 25% low compared with what it should be. If A and B agreed, all the points would be on the line of identity. The fact that they're below the line of identity means that set B is giving a smaller value. So an excellent correlation and a linear trend line doesn't necessarily mean that the two sets are in agreement. In fact, a 25% disagreement between the scales here would be very important. So if you need to compare two measurements of the same thing on two different instruments, don't use the correlation coefficient. That's totally pointless. What you can do if you want to test overall agreement is to use the paired t-test. That is a way of testing two numbers to see whether they are actually in agreement. If you need to use a non-parametric test, then Wilcoxon's matched pairs sign rank test is the alternative, and we've talked about both of those in previous lectures. But another way is to look at the slope of the trend line. In that example I just showed you, the trend line had a slope of 0.75, which is very much less than the slope of the line of identity, which is a slope of 1, and that was clearly brought out by putting the line of identity on the same plot. All of those are ways of showing that there is disagreement between the two measurements. Another way of doing this is the Bland-Altman plot. In fact, this is an ideal way of showing if there is any disagreement, where it occurs. Now, the Bland-Altman plot is used when we're comparing two measurements, x and y, that are supposed to be the same. We plot a graph showing how the difference between the two measurements, x minus y, varies with the true measurement. Quite often we don't know the true measurement. We have two measurements, x and y, but we don't know which is correct. So in the absence of the true measurement, use the average of x and y as the best estimate of the true measurement. Then you plot the difference, y minus x, on the vertical axis, and the average, y plus x over 2, on the horizontal axis. Here is an example of a Bland-Altman plot. On the left we've got the ordinary scatter plot with y on the vertical axis an X on the horizontal axis and the diagonal line showing the line of identity where Y is equal to X. Each of the circles shows a measurement, and some of them are above the line of identity and some are below the line of identity. So they're equally scattered about it. There is no obvious trend. The vertical bars show the distance of each measurement from the line of identity. But if we replot the same points on the Bland-Altman plot, now on the vertical axis we've got the difference, y minus x, and on the horizontal axis the average, y plus x over 2. Once again, the vertical bars show the difference of each measurement from the line of identity, because on the Bland-Altman plot the line of identity where y equals x corresponds to 0, the horizontal line going right through the middle of the data. So the Bland-Altman plot is just displaying the data to show how it varies about the line of identity, and any small differences from the line of identity are much easier to see on the Bland-Altman plot than they are on the scatter plot, because the line of identity has a big slope and small differences from it are difficult to see. So once again, on the Bland-Altman plot we can see that the points are distributed equally above and below the line of identity, just as they are on the scatter plot. But the Bland-Altman plot shows up any systematic differences and makes them much easier to see. Here's an example of a Bland-Altman plot which has the points scattered randomly above and below 0. So there is no systematic difference between y and x. The difference y minus x is sometimes positive and sometimes negative, equally so, and it doesn't change with the horizontal scale. So this is a perfect result for the Bland-Altman plot, showing there is no systematic difference. But here's another example of a Bland-Altman plot. I wonder what we can deduce from this. Just think about it for a moment and see if you can work out for yourself what you would deduce from this plot. As you can see, all the points tend to be above 0, so y minus x is always positive, it's never negative. If y minus x is positive, that means that y must be bigger than x. So here, y is consistently greater than x over the full range. That shows a systematic difference between y and x, and the Bland-Altman plot clearly shows that up. Here's another example of a Bland-Altman plot. What could you deduce from that? Just think about it for a moment. Obviously a lot of the points are above the line and a lot below the line, so it's not consistently above or below. But at the left-hand end it tends to be below 0, and at the right-hand end it tends to be above 0. So that says that y is smaller than x at low values, because for low values y minus x is negative, which means y must be smaller. But for large values y minus x is positive, which means y must be bigger than x. So we have a difference between the two measurements, which changes as the measurement changes. So at one end y is smaller and the other end y is bigger. Here's another example. What could you read into this sort of Bland-Altman plot? Well, here again it's not consistent about 0, but for low values it tends to be okay. It's at high values it veers towards the negative. So the y and x agree at low values, but as the measurements get larger then y tends to be smaller than x, because y minus x is negative. That means that y must be smaller. So these two measurements only agree at small values and tend to deviate at large values. Here's another example. What about this one? Well, there doesn't seem to be any significant difference above or below 0. There are just as many measurements above as below, so there's no consistent trend. But for large values they're very close to 0. For large values, they're much more spread out. So what we can see here is that at small values there is an increased variability between y and x. The measurements are less reliable. There's no systematic difference, but the differences just become greater. The measurements are less reliable at small values. So you can see the Bland-Altman plot can tell you an awful lot about the difference between two measurements if they're supposed to be in agreement. Let's do a worked example with left ventricular ejection fraction. Supposing we've got two different programs for analysing MUGA, that is cardiac gated data, which are designed to measure left ventricular ejection fraction in nuclear medicine. So we want to know, do the results of these two programs agree in measuring left ventricular ejection fraction with the same data? So we've got 15 MUGA studies analysed by both programs. And of course they should both give the same result. We can compare the means using a paired t-test, we can draw a scatter plot, and we can certainly draw a Bland-Altman plot. All of those will be useful. So here is some hypothetical data. Program A gives these measurements for ejection fraction, and program B the others. So for the first patient, program A gave 49% and program B 50%. For the second patient, program A 34% and program B 36%. So for the paired t-test, we need to pair those numbers and calculate the paired t-test, which we've discussed in a previous lecture. I'll just show you here the result of using Excel's data analysis tool for a t-test paired to sample for means. This is the output that you get in Excel using that tool. And you can see that it gives a highly significant difference. For a two-tailed test, the p-value is 0.004, highly significant, saying that there is a difference between the results from program A and program B. Yet if you look, this output also gives you the Pearson correlation coefficient, R, of 0.996. That's a very good correlation, showing that these two results are correlated. The answers from program A and program B are highly correlated, but there's a highly significant difference between them. How can that both be true? Well, this is illustrating just what I was saying, that correlation and agreement are not the same thing. You can see that by plotting the scatter graph. Here we've got the left ventricular ejection fraction by program B on the vertical axis and by program A on the horizontal axis. And you can see there's a jolly good straight line through all those points. The correlation coefficient of 0.996 reflects that. So we can see there is an excellent correlation, but why is there not good agreement? That's what the paired t-test says. Doesn't look like there's any disagreement between them there. You'd say they're pretty good. But remember, I said the scatter plot can be misleading, and the Bland-Altman plot is a better plot. Here, if we look at the line of identity, it becomes a bit clearer as what's going on. Although we've got a straight line through these points, they don't follow the line of identity. The Bland-Altman plot is basically telling us how far away all these points are from the line of identity. So here, for the Bland-Altman plot, I have to calculate the average and the difference. So I've shown here A plus B over 2, 49 plus 50 over 2 is 49.5, and A minus B, 49 minus 50 is minus 1, and so on. So the Bland-Altman plot consists of a graph of this difference A minus B against the average A plus B over 2. And that's what I've shown here. The average LVEF goes from about 20 up to about 75, and the difference goes from about minus 7 to a plus 1. You can immediately see here that A is less than B when the average LVEF is below about 40%, but above 40% there seems to be good agreement between them. So that illustrates that there is overall a significant difference, but it only occurs at values below about 40%. So the two programs are in agreement for good ejection fractions, but as the ejection fraction gets small, the programs diverge. There's a significant difference between them. That's why the Bland-Altman plot is so useful for illustrating this. So our conclusion is that we've got a strong correlation, R squared is 0.996 between the two programs, but that doesn't mean anything at all. Because these were two measurements of the same thing, they will always be correlated. The paired t-test shows that there is a significant overall difference between the two programs with a p-value of 0.004, and the slope of the trend line, although it's close to identity, is not perfectly identical, and so the difference is hard to see. But if we use the Bland-Altman plot, then that highlights where the difference occurs, and it shows that there is good agreement for LVEF above 40%, but program A gives a lower value for LVEF at less than 40%. So that's how the Bland-Altman plot can be very useful in showing differences in agreement between two measurements of the same thing.